Here we go. So what are we doing today? Well, we're going to prove a theorem. One theorem, and this is from page 734 of your book. This is theorem 58.5 on page 734. I guess I have the book open, right? I could take a peek that way. Oh, I got to go back a few pages. Yeah. So the first 4 pages of this section are basically getting you ready for the theorem. And then part C, proof of the existence and uniqueness theorem. And here's the theorem. All right? Guys, don't write this down. Write down what I write down. I mean, it's the same. That's beautiful. And it says, see figure 58.57. That's this picture. Where'd they put it? Here. We're going to use this picture a lot. All right? So I'm going to talk you guys through this. I think it'll be good. So here we go. The theorem. Let f of xy be bounded and continuous in a region S. Let x naught, y naught. If I write this, do you guys know what this means? No, I'm sorry. That's math notation. That means is an element of. So, is an element of S. What's the picture? First of all, what class are we in, basically? Calc 1, Calc 2, or Calc 3 at this point? How do you know we're in Calc 3?
Oh, because it's
Okay. There's 2 inputs, right? So what's the graph going to look like? How many dimensional? That's why we have this kind of a picture. You guys understand that? Now, when I say that the function is bounded and continuous, I claim that as Calc 3 graduates, you guys know continuous. You understand that to some extent. What does bounded mean? What?
between.
Yeah, between what and what? Means it doesn't go to infinity. Okay? Some functions zoom on as high as infinity, right? This one doesn't. This one's bounded. So it's a surface, let's say. At least it has to be bounded over a region S. You guys, the picture here, maybe I can go down a little bit. Yeah, see, they did. See that little circular region? That's S. So picture my function. I mean, they don't graph the function because they wanted to show you everything else going on. But the function is kind of like a Calc 3 kind of surface above S. Does that make sense? Okay. And then when we say x naught, y naught is an element of S, that's just saying pick any point in this region somewhere. Well, they happen to pick this point. See it? X naught, y naught? Okay. So we're going to do this. Oh, next. Suppose that in S, the function satisfies what is called the Lipschitz convention. That's one word, guys. Lipschitz condition, let's say. And the Lipschitz condition would be absolute value of f of x comma y minus f of x comma y bar is less than or equal to n times y minus y bar. Whoa. So I think I'd better take at least a moment to explain the Lipschitz condition. Okay? Now remember, in your book, what part of the lesson is this? This is 58 part what? This theorem is 58 part C. Okay? Part A is all about sequences of functions. Part B gives you other things that you're supposed to know for this theorem, like the Lipschitz condition. What the heck is that? All right? Guys, I don't want to spend more than one day on this. So I don't want to go crazy with this stuff. But I will say this. I will say that the Lipschitz condition, this is a very reasonable restriction. Probably if I just say, hey, name a function, your function is going to satisfy the Lipschitz condition if it's continuous. Okay? So this is kind of technical, I guess. But let's say what the conclusion is then. Then, there exists an interval I-O given by absolute value of x minus x naught is less than h, and here h is bigger than 0, such that are you guys okay with the backwards E for there exists? It's just shorthand. You could write out in English if you want. I'll write everything else out in English. Such that there is one and only one continuous function y of x with a continuous derivative on I. It's funny, they put I-O. Jimmy asked me before for the other problems, what's I? And he said, oh, it's interval. They put I-O. Do you guys know what the O stands for? What kind of interval? Open interval, that's right. These are open intervals. Okay, one and only one continuous function on this interval satisfying, and I'm going to write the conclusion here in a different color just to emphasize. Satisfying y prime is f of x comma y, and do you know what else I'm going to write besides that? What class are we in? Diffie Q. What is this? That's a differential equation. What order? First order. If I want to get one and only one solution, I need to add what to it afterwards? An initial condition. Do you know what I'm going to write for the initial condition? I'm going to write y of x naught is equal to what?
0.
Yeah, you could. I'm going to write y naught because I figure why not? No, because then it's more general. But a lot of times it's 0 in these problems, and then those are easier. Okay. Wow. That's a huge mouthful of a statement. So maybe I should ask, are there any questions before I move on? And we're already at 10:48. That's amazing. And I've only stated the theorem. But I like going slowly. A lot of professors write it down and go.
What's the Y bar stand for?
So Y bar, I guess you're going to see it's a particular Y value, different from Y initial. Okay? We have to wait and see. I guess think of it as any other Y value besides whatever Y is. You guys cool with this being an interval? Because, like, how do you solve absolute value inequalities? Like, what's the picture? Do you guys know what the center of this interval is? Okay, so this is worth showing now. Oh yeah, Joe?
Would it be X naught?
That's right. X naught is the center, and then H is kind of like the radius. This will go as far as X naught plus H, and it'll go as far as X naught minus H. Should I show that real quick? Yeah. So how do I show that? Maybe I'll just do it over here on the side. Look, guys. If you wanted to solve X minus X naught in absolute value is less than H, you could take away the absolute value bars as long as you're less than H and also greater than what? Actually, you could be even smaller than 0. Negative H. Because, boy, how do I convince you of that? Well, here, like take, let's fill in some numbers, you know. Let's try, hey, is it true that the absolute value of 3 minus 5 is less than 3? Well, yeah, it is. Because 3 minus 5 is less than 3, but it's also greater than what? Negative 3. But see, if I try this, is it true that 3 minus 50 absolute value is less than 3? Is that true or false? That's false. And the reason it's false is because it's not greater than negative 3 when you take away the bars. See that? So maybe that kind of shows you. But this is a common algebra move, is you take away the absolute value bars and you get 2 inequalities, and then you just solve for x by adding x naught to every side. So this would be x naught minus h. But when you work with inequalities a lot, it's a really nice trick to just be able to go from here to the picture. That's an interval. So I like showing calculus students that in Calc 1 when we do it. And then, you know, just thought I'd remind you of it here. Okay? So the goal today is to prove this. To prove this theorem. It'll be our one special case of existence and uniqueness. Is it true that existence and uniqueness happens for second order? Absolutely. The difference, how many initial conditions do you need? 2, and then you get 2 constants you solve for, right? We've done that before too. You could modify, I think the proof is in your book if you really want to look at it. I don't think you do. I think we'll look at this proof and we'll say that's enough. All right? So here we go. We're going to write down the 4 parts of the proof, then we're going to take a break for Preston and whoever else needs it. 4 parts of the proof today. Ready? Your book is really good about this. They break it down into steps. So part A. Part A of the proof is this. We're going to show you how to determine the open interval. That's what part A is. Because I said this interval exists. Part A is just show me how to determine it. Part B. we're going to prove that each Picard approximation, that's why I needed to do this last time. We're going to prove that each Picard approximation is continuous and that its graph lies in a rectangle R, which is contained in S. So let's show the picture again for a moment. Here's the picture, right? See that R that's shaded? Notice that's within S. So what we're going to do today, we want to show that there's a unique solution, right? Y, what are they going to call it? Y of X. Here, let me go back to the, right? It says there is one and only one continuous function Y of X. This is what we're trying to prove. Where's it going to live? I'll show you how we're going to get it. We're going to start doing Picard approximations like we did last time. Each one of them is going to live in the rectangle, which lives in S. And then, here's how the proof works. Part C, we will show that these approximations converge uniformly. This is why I had to talk about uniform convergence. Uniformly to some Y of X which is a particular solution. So we're going to show that. We'll show the Picard approximations converge uniformly to something which is the particular solution. So I guess the question is, why is there a part D? Well, you have to look carefully at what's being claimed. So this is the conclusion, right, guys? Have we done everything yet? Let's see. Then there exists an interval, we did that, such that there is one and only one continuous function Y of X with a continuous derivative satisfying this stuff. Well, part D, and this is very, very common when you prove mathematical theorems, we will separately establish uniqueness. Why? And that's what it's called, right, guys? What's the theorem called? What kind of theorem? Existence and uniqueness. Guys, when I say there is one, that's existence. And only one, that means not more than one, that's uniqueness. You get that? So the way you prove the theorem is first you establish existence, then you establish uniqueness. And then we go from there. And it's time to pause for our abbreviated break today.